My name is Max Torres Rivera, and I'm a student from Physics Lab 2, known as SCI 1441 OL.
The lab experiment we are doing is the RLC circuits lab number 8. In order to complete this lab, we will need our Espotec Labrador board. We'll need a 1K ohms resistor, a 100 NF capacitor, a 100 mAh inductor, our jumper cables, and breadboard. For our first part, we're going to need the Espotec Labrador in order to complete our first 3 data tables. We're going to use our Espotec Labrador, and when we connect it to our laptop, we're going to have this display on the application. The connections for that Labrador are on this picture below. So for our first table, we put that the frequency was 3 kilohertz, our resistance is 1000 ohms, our inductor is 100 mAh, and our capacitor 0.1. And we obtained these values over here with our 2 channels. You plug in those values on the data table that we get from all those values. We do the same for data table 2 and 3, but here we change the frequency. It was first 3000 hertz and now it's 1000 hertz. We do the same, we plug in our values, and we do the same for data table 3. Here we use 1.7 kHz instead of 1000 hertz that we use on the second table. And I'm going to show you the examples of the computes that we did in order to obtain those values. So we put our given values on each data table. On data table 1, we have that our frequency was 3000 hertz, our resistance was 1000 ohms, our inductor was 100 mAh, and our capacitor was 0.1. So we plug in the formulas to find XL and XC. Then we find our tangent, the accepted value, and we use the formula arc10, and we put our value from 10 that we already got to have our degrees in RADs, radius. After that, we calculate our percentage error, and we'll plot all those values on the data table 1. We keep doing the same for data table 2. We put our given values, in this case 1000 hertz instead of 3000. We do the same steps, and we also get our percentage error. We do the same thing for data table 3. Instead of 1000 hertz, we got 1700 hertz, or 1.7 kHz. And here we do the same steps, but after we plug in our values, we have to find our FR. We get this given value, which is 1 divided by 2 pi times square LC. We'll get our frequency, and then we'll do our percentage error, which is the same formula from the other 2 tables, and we'll get the percentage error. And all these 3 tables are done with the Espotec Labrador. I'll show you again the pictures. When we take the values, data table 3, and you can see our frequency over here, 0.7 kHz. Data table 2. You see that we have the 1 kHz, 1000 hertz. And for data table 1, we have the 3 kHz, or 2.98 to be exact, 3 kHz. That's the first part of our lab. Now we go to the second part. In the second part, we're going to need the application known as FallStat. This application will let you create diagrams and simulate them and see how they react. So So what we do, I'm going to show you live how we do it. I already have this diagram created. I have my AC source, I have a resistor, an inductor, and a capacitor. So you can edit the frequencies and anything you want here. In this case, I'm going to leave it 1.6K frequency, but you can change it if you want. And you can simulate it. Press the run, stop button, and you can simulate. What I did here, in order to obtain this three-dimensional X and Y scope, is that you can edit this. You can edit your AC source, and you can view. I'm not going to tap because I don't want to get it, but you can press view in new scope, and once you do that, it will allow you to see the scope, and you change it to X and Y. And you have when you run the simulation, your live values and how all the voltages in turns are behaving. And you have this indicator which will tell you your voltage, your VX, your voltage in X. Over here, VX. You already have your values of Vmax, your current values, your wavelength. It gives you everything. And you can change the values, like in one table that's 1.6 kilohertz. You can edit it, and let's say you want to fill in the 3000 hertz or 3 gigahertz one. You apply it, and it'll be faster because you obviously put a higher frequency. It'll change your wavelength, and it'll change all your values. You can do the same for the 1 gigahertz one. Like, that's how you do the scopes. You go to your properties and you can the X and Y codes. That's how I did the first scope. You can remove it also. So yeah, you have the 3 gigahertz one. You can change your last table. 1K or 1000 hertz. Change the behavior, wavelength, everything. So that's how we get our initial data. We're filling out data table 4, 5, and 6. So I'll show you values for those 3 tables. So here is for data table 4, it asks you for the 3000 hertz frequency, which I have over here. The AC frequency, 3000 hertz. I stopped the simulation and I took a screenshot of the values. So my VX is going to be here, 2.118 voltages. I already have my max voltage, which is 2.5, so those are the 2 values I have to plug in. I also did 2 images of different behaviors on the diagram, like it was asked on the table. Include 2 images of the VX and Vmax values. I plug in those values, and then I use the angle of the phase in radians that I had on data table 1, which was 0.94, and then with that value, I use this formula: angle in radians expected, sine inverse or arcsin Vx divided by Vmax, and I got this value, and then use the other formula to get your percentage error. And you keep doing the same for each table. Data table 5, zoom in real quick, it says 1 kHz, and I put the 1 kHz on, and it gives me these values over here, the AC source and everything. My Vx, again, this one, I'll plug in the values. I got the other picture that was required, and I plug in my values, and I do the same for the other data table. These are the symbols of the computes. data table 4, I put my given values, apply the formulas, and I'll get my accepted angle and the percentage error. And I do this for data table 4, data table 5, and data table 6. In this laboratory practice, I analyzed the phase relationship between voltage and current in RLC circuits under different conditions, inductive, capacitive, and resonance. This lab was super helpful because it helps you understand the AC circuits, analyze them, the importance of basic electronics, and the practical use of laboratory instruments for measuring and interpreting electrical phenomena.